Class recording has started. Now I'm going to move the microphone. It's going to make a bad It's going to sound like a hurricane. Actually, I shouldn't make hurricane jokes anymore, seeing as how we actually have. But anyway. All right. If we zoom in on the calendar, if you're watching at home, you don't get to see the zoom because it doesn't happen on the monitor over there. It only happens up here. So, But anyway. First, test corrections. If you haven't turned in to be test corrections from the previous test, the Force Newton's laws test, please make sure that you get those in sometime in the relatively near future. Today. See how it's now 45 seconds after I asked the first time. There's even more urgency to get them turned in. So, all right. Then Wednesday, you guys took a quiz over impulse momentum. We're going to talk about that quiz in a little bit because there's a couple of questions that I want to make sure that we clarify. Then you gather data for your next lab, the Conservation of Momentum Collisions lab. We are going to talk about some problems later on today dealing with that lab or that are similar to that lab. So, today, some conservation of momentum problems in one dimension. Like I said, I want to do a couple of examples that are similar to what you were doing in your lab so that when you go to do the calculations for your lab, hopefully they're not, too foreign to you. Okay? Then, next week, right now, I have a review scheduled for Monday and then test Tuesday, but I do think that's pushing it a little bit. So, we'll do some more problems on Monday. Tuesday, before break, we'll do some kind of review activities. There's a couple of videos that go along decently with what we're doing here, so we might watch a little short video. And then we'll come back and we'll test on Tuesday when we get back because testing on Monday is obviously not conducive to you doing well generally. So I will change the calendar today to make sure that that's updated so you can get that there. Okay. Wednesday, I think it was yesterday morning, I posted objective sheet. So it's up there, you can check that out. It has a list of problems that relate to this section, broken down by topic, so you can use that to help start studying for your test. Also, you got your quiz. That obviously will help you study as well. Okay. If you have not completed the previous lab, the impulse momentum lab, please get that into me as well. Obviously, that will help you study for your test doing that too. Okay. Questions? All right. Lindsay, will you go outside just for a couple seconds? We're going to talk or quiz. Anybody else not take a quiz? Okay. As far as the quiz is concerned, there are two questions that I would like to talk about because actually it's three questions total, but two questions that I wanted two sections. All right, so let's start with number 10. Let's start with the calculation problem. Okay. More people in this class got this problem right than in the previous class, but seeing as how there's only one recording, I want to make sure that we cover it. Okay? So first, this problem is asking you to solve for force, right? So the force is your unknown here. We've only had one equation up when we took this quiz. We only had one equation up until that point, right? And that was your impulse momentum equation. Sigma F delta T is equal to M times delta V. Okay? The important thing being here that in the second sentence it says the ball was originally traveling 10 meters per second, and after it was hit, it was traveling 36 meters per second in the opposite direction. Meaning, what has to be true about VI and VF? One has to be positive and one has to be negative, right? When we break this down, when we break the change in momentum down, V final minus V initial, right? That's always the case. You can't change the equation. But when you go to plug things in, if you call the direction that the ball was originally traveling, okay, as positive, that's V initial. So minus a positive 10. But it tells you in the problem, opposite direction after it was hit, so that means the final velocity, negative 36. So negative 36 minus positive 10, mathematically, you're going to do what? Subtract, but a positive number is like whatever, okay? The point here being, what number are you going to have inside the parentheses? Negative 46, okay? Not 26. Okay? And that's where you get it when you plug it all out. That gets that there. The mass was 0.06. The time was 0.02. You solve for force. You end up with force being negative 138 newtons. Okay? Questions there? I think most people who didn't get that probably saw that kind of quickly. So, all right. The other problems that I wanted to talk to you about were on the same side, but up at the top. So it says, a rotten apple dropped from a height of 1 meter. It squishes when it hits the ground and it stops. It says a 1 kilogram rubber ball. Color request on the rubber ball?
Blue.
Blue. I was just going to say just not red because that's the apple. Oh. Too bad.
Green.
All right, 1 kilogram rubber ball dropped from a height of 1 meter. When it hits the ground, it bounces back up to a height of 0.85. Last, a 1 kilogram lump of Play-Doh. What do I want to do here?
Yellow blob. Yellow
Yeah, just make it a circle.
What?
Make it a
Yeah, because I put it on auto draw, so it like corrects me, like makes triangle if I do that. You know, so that's how I make these circles here, right? So. Glad we got this on recording. So. So 1 kilogram lump of Play-Doh. Color requests on the Play-Doh?
Yellow.
Yellow.
Brown.
Purple or something.
Green.
Brown is like what color Play-Doh turns into after the first time you play it, and all just gets mixed together. Like, you know. We'll go yellow. So. All right. So there we are. Okay. Play-Doh bounces, but to a real short height. Okay. If we drop them all from a height of 1 meter, what are we able to assume about when they get to the ground? Same time, but also from a velocity standpoint, the same velocity, right? So they're all going to fall. Ooh. There we go. There we go. That really. Now this totally isn't worth it, but that's okay. Okay, so apple falls, ball falls, Play-Doh falls. If we drop them all at the same time, they would get to the ground at the same time, and they would get to the ground with the same speed. But it says, right, the apple squishes and stays there. The rubber ball bounces back up, not quite to the height that it started from, but still pretty high. And then the Play-Doh only bounces just a little bit. Okay? Out of those three, first, when does the impulse start that we're talking about here in this problem? The impulse starts when what? When they get to the ground, right? That's the change in momentum that we're concerned with here. Out of these three options, right? No bounce, big bounce, and short bounce, which of those is the biggest change in momentum? Big bounce is the biggest change in momentum. Similar because of the reason that we just talked about in the last problem, right? Negative velocity initially, positive velocity final, right? But if it bounces higher, the velocity after the bounce has to be bigger than if it bounces just a little bit. Does that make sense? Okay. So the blue one experiences the biggest change in momentum. That's the answer to number 8, right? But if number 7 asks you about the greatest impulse and number 8 asks you about the greatest momentum change, what has to be true about the answer to those two questions? Has to be the same answer, because impulse and momentum change are the same thing, right? So, things bouncing, things turning around and going in the other direction, that is a large change in momentum. That requires a large impulse. We said there's basically two ways that you can do large impulse, right? What are the two ways that we can get a large impulse on something? Impulse depends on two things, yes? That's changing momentum. What does impulse depend on? Time and force, right? So we can apply a smaller force over a greater time, right? Or we can apply a greater force over a smaller time. Obviously, if we do greater force and greater time, that's the biggest change in momentum, but we see that we can mess around with those two factors. Okay? Questions about those problems on the quiz? Do we understand why 7 and 8 have to be B and B? Okay? Go ahead, Rick.
Right? I put D. When you circle B and then said okay.
Okay. On the quiz, if you circled an incorrect answer for number 7,
Same one.
okay? As long as you circled the same one on 8, I gave you credit for 8 because at least in theory, you knew that impulse and momentum had to be the same thing. You may have just been blindly guessing, but that's, on me, okay? But yeah, if you circled, A and A, I gave you credit for 1 because you knew that the two of them had to be the same. They're wrong, but at least you knew that they should have been the same answer. So that's what I did as far. So if you see on question number 8, if you have something if your answer isn't, if I circled a different answer than your answer, but I wrote okay next to it, I gave you a point because at least you knew that the two of them were supposed to be the same. Questions? Other questions relating to the quiz? Ted, go ahead.
For 5, isn't it the same amount of force but more time that it's going
So for 5, right? Ted, here's a situation where if you're jumping off a platform and you jump to the ground, eventually what's going to happen to you?
I'm gonna stop.
You're going to stop, right? Meaning that if we go back to this equation, right? Unlike when things bounce off the ground in the previous problem, here, the change in momentum that you experience when you come to the ground is going to be the same whether you bend your knees and land softly or whether you do that. Okay? Does that make sense?
Wouldn't it take more time to land?
If you bend your knees, yes. But if the momentum change is the same no matter what, that's when we see the inverse relationship between the force and the time. Okay? Now, keep in mind, that's not the same thing as we just talked about in the last problem, right? Because in the last problem, the momentum change of those 3 things wasn't exactly the same for all situations. But in this case, you landing on the ground, whether you land on your feet and bend your knees, or whether you land on your feet straight leg, or whether you fall off the ground and land on your butt, the momentum change is the same no matter what, because you got to stop.
Okay.
Okay. All right. Other questions? Quiz? Okay. If you would please, you can put that quiz away. You're going to need something to write with, calculator, notes from the other day if you took any, and then I'm actually going to do a couple of example problems out of the book. If you want to copy the book, there's extra copies over on the ledge. If you just want to look it up, I'm going to show it up on the board, so if you just want to look up here, that's fine too. Okay? So something to write with, calculator, notes from the other day, copy of the book if you would like it. Go. been a couple of days since we discussed these topics. Let's review briefly. On Tuesday, at the end of the period, we introduced the concept of conservation of momentum. And we talked about the idea that conservation of momentum means that however much momentum we start with in a situation, we have to end up with. So sigma pi equals sigma pf, right? The total initial momentum has to equal the total final momentum. Remember, p representing the momentum of an object. How do we calculate the momentum of an object? Mass times velocity. Okay? So p itself is mass times velocity, but when we talk about conservation, we have to talk about all the momentum at the beginning and all the momentum at the end.
Why does P stand for momentum?
When they were first developing the concept, like when Newton was sort of developing these things, it was referred to as progress instead of momentum, and so that's kind of where the P comes from. So,
in
that's,
sense, we already have
M
M for mass.
Yeah, we have M for mass, and so that's what I've heard as far as that goes. So. And M for meter, and it's just M's kind of played out. So. All right, are we good with this idea? And we looked first at this picture, right, where the cue ball came in, runs into the 3 before the collision, right? The cue ball had momentum, but the 3 ball did not, because the 3 ball did not have any velocity. But after the interaction, right, cue ball stops, 3 ball starts moving, so all of the momentum is transferred from the cue ball into the 3 ball. But I think we made the point that the velocity doesn't necessarily have to be the same unless what? Unless the mass is the same. So the momentum has to be the same, but momentum is 2 factors. Good there? And then we talked about get rid of this. Apparently we can't. The X is over there on the side, but it's being hidden right now by this. Whatever. Alright. Then we talked again about striped girl and blue girl, right? And we said that here they both start with 0 momentum, but they both end up moving after their interaction. And we said, okay, it looks like there's 0 momentum to begin with, but there is, and at the end, because momentum is a vector, those cancel each other out too, right? But we said the important idea here is the reason that happens is because, according to Newton's 3rd law, the forces that those girls feel are equal. And the time that they feel that force 4 is equal. So if force and time are equal, what does that mean has to be the same for both girls? Because force and time, we already established earlier, force and time is what? Impulse. So if they have the same impulse, right, that means they also have the same what? Change in momentum. Except one's positive and one's negative, right? Example that we didn't get to on Thursday. Right? This gun. Anybody ever fired a gun before? I think we talked about this. So, important part of firing a gun, right, is making sure that you account for the recoil of the gun. Because if you don't, it can hurt you, depending on what kind of gun you have and stuff like that. Right? But same situation as the girls, right? Before you shoot the gun, bullet and gun are both at rest, so they both have 0 momentum. Afterward, the bullet has a large positive momentum, but to make the total come back out to 0, what has to happen to the gun? It has to have some negative momentum, and that means it has to have negative velocity, so it has to go in the other direction, right? But, as we discussed, right, There's internal forces there, action, reaction. You feel, the bullet feels a force, the gun feels a force. How much? Same force, but opposite direction. Okay? And that means their momentum has to be the same, but not necessarily their velocities, right? If the large arrow represents momentum, those two arrows are the same length, but the smaller arrows representing velocity don't have to be the same length, because we take into account that mass factor as well. Okay? Good there. All right. Let's take a look. Sorry, don't feel writing things down. Actual writing of stuff down. I know it's using a novel concept. So while we're writing those things down, anybody ever shoot a handgun versus a rifle or a shotgun? Okay. Recoil on your rifle is a lot more than the recoil on the handgun. Yes.
Depends what size.
Depends what size the slug. Yeah, that helps. But generally your recoil on a rifle is going to be bigger than your recoil on your handgun. Generally speaking. Yeah. If we look right, if we go back to this picture. This picture. Okay. So there's the bullet in the chamber, right? There's the gun. Okay. On the rifle, are we all somewhat familiar with how a gun works? Okay. There's an explosion in here basically, and then the explosion pushes the bullet one way and pushes the gun the other way. Okay. But in the rifle, because the barrel is a lot longer, that allows the explosion to push on the bullet for a much larger time. If time is increased, right, what's that going to do to the change in momentum of the bullet? It's going to increase the change in momentum. Generally, bullets go a lot faster out of rifles than they do out of handguns because of that fact that the bullet gets a force exerted on it for a much longer time. So that means that the recoil on a gun, a rifle, is generally bigger than the recoil on a handgun because of that larger change in momentum of the bullet. Good there? All right. If you have your book, I'm going to go to page 210. I'm going to go to page 210. If you don't have your book, I'm on page 210. So, page 210, there is a section right in the middle of page 200, or actually at the top, that's called Practice Problems. We are doing practice problem number 12. You just read that, or do I need to make it bigger? Bigger. Okay. So, it says a 0.5 kilogram ball traveling at 6 meters per second collides head-on with a 1 kilogram ball moving in the opposite direction at a speed of 12 meters per second. The 0.5 kilogram ball bounces backward at 14 meters per second after the collision. Find the speed of the second ball after the collision. All right, so what are we looking for? Which speed? Final of which ball done? Second ball, right? So we are looking for V final of ball 2, right? That's our unknown in this problem. Okay? I'm going to make myself two lists, one for ball 1 and one for ball 2. Okay? All right, some things we know here, right? Start listing them. I'll start listing them up here. What are some things we know that are going to help us start this problem off? Okay? So, they gave us the mass, right? So that we know that the mass of ball 1 is 0.50 kilograms. And the mass of ball 2, 1.00 kilograms. Okay. They told us what was going on before the collision, right? They told us that the initial velocity of ball 1 was equal to 6.0 meters per second. that the initial velocity of ball 2 was 12 meters per second. And they told us that after the collision, the final of ball 1, ball 1 traveling at 14 meters per second. Okay. Good there?
Oh no, isn't this supposed to be like a drill or something? For like instruction? Don't know. Is that Mr. Clark?
Ambulance?
11:45.
That's what Mr. Clark said.
Yeah.
Alright. Okay. Do my visual people need a picture to help us out in this situation?
Please.
Okay. Picture it is then. So, ground. There's ball 1. Ooh. There we go. There's ball 1. What?
So is everyone in that thing or demonstration?
What?
Never mind.
What demonstration?
I thought. Never mind.
Okay.
I thought I was cool.
And there's ball 2. Okay. Notice it's much larger size, right? Alright, that's probably a little too. Alright, and we'll make that one blue. Okay. So it tells us that ball 1 is moving at 6 meters per second, right? Before the collision. Ball 2 moving at 12 meters per second, but it tells us because it's a head-on collision, what has to be true about this object? Which way does it have to be going? The other way, right? So, right, it's going in this direction, yes? Then, after the collision, there's that, and there's that. It tells us that ball 1 goes in the other direction at 14 meters per second, and it wants to know what's going on here. Yes? Before, after. Okay. What causes these two things to change what they're doing? Impulse caused by what? In order to have impulse, we have to have force, right? Where do the forces come from in this problem? What do they have to do? Hit each other, right? So, Katie, if they hit each other, what's true about the forces that they feel? They're equal forces, right? Newton's third law. If they're equal forces, they're equal impulse. If they're equal impulse, equal change in momentum. So that leads us to the fact that momentum is going to be conserved in this problem. The total initial momentum has to equal the total final momentum. Okay? Good there? Right. Now, you don't have to show me this every single time. Sorry, one thing we should do before we do that. Based on our picture, we should probably make some changes to the information that we laid out in order to help us solve this problem, right? Like, for example, we established the fact that blue is traveling in the opposite direction as red. So what should we do with blue's initial velocity? Okay? It's got to be different. So in this problem, if we call the positive direction to the right, negative direction to the left, blue has a negative initial velocity. If red bounces off and starts going in the opposite direction, what has to be true about red's final velocity? It has to be negative as well. Can we assume that blue's final velocity is positive? No. Okay? You don't know anything about blue's final velocity here. If you do the calculation, it will come out to the sign it's supposed to come out as. So don't make that assumption. Just plug in the numbers that you know and let the answer come out the way it's supposed to come out. Good for starters. Okay. Same force, same same time, same change in momentum, blah, 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 blah. Momentum is conserved. Not that you have to do this every time, but if we're calculating the total initial momentum, right, we have to figure out the initial momentum of ball 1 plus the initial momentum of ball 2. That's what the sigma means, right? It means add, it means sum, it means total. Together, those two things have to equal the final momentum of ball 1 plus the final momentum of ball 2. Going from this line to this line is exactly the same thing. We're just applying the conservation idea to our specific problem. Good there? Now, we established earlier, what do we know about momentum? How do we calculate the momentum of an object? Mass times velocity. So if we want the initial momentum of ball 1, we need to know ball 1's mass and ball 1's initial velocity. Again, if we want to know the initial momentum of ball 2, ball 2's mass plus ball 2's initial velocity. That has to equal ball 1's mass but times ball 1's final velocity plus ball 2's mass and ball 2's times ball 2's final velocity. Does that make sense where that all came from? How we went from the top line to the middle line to the next line. Okay? That's conservation of momentum right there. For two objects. If you had a third object that was involved in this interaction, how many terms would you have? You'd have 3 on each side. Initial 1, initial 2, initial 3 equals initial 1, or final 1, final 2, final 3. Okay? Now, we start looking at it, right? What did we say we were trying to solve for originally?
Final velocity.
Final velocity for ball 2. This is our unknown right here. Do we know the mass of ball 1? That was given to us, so we know this one and we know this one. Do we know ball 1's initial velocity? Yes. So we know that one. Do we know the mass of ball 2? Was given to us in the problem. So that and that. Do we know ball 2's initial velocity? It was given to us in the problem. Do we know ball 1's final velocity? We do. Now we can start plugging in things and solve for V final of ball 2. Why don't you do that? Find out what V final of ball 2 is. its final velocity is -2. What does that mean happened when the two ran into one another? They both are now going in the same direction. Ball 2 is still traveling towards the left, just not as fast as it was before. Okay? It had enough momentum to keep going through and continue on in the same direction, even as it bounced ball 1 back the other way. Good there? Okay. Next, on that same page, problem number 9. So this is still page 210, and this is problem number 9. The reason why I want to do this problem, that example problem that we just did, is similar to one calculation that you need to do in your lab. This one is similar to another kind of calculation that you need to do in your lab. Okay? I realize the bell is going to ring, so here's what I will do for you guys. Okay? I will stop the recording now. When you all leave, I will finish the recording and then I will post it so you can see how I do this example. Is that okay? Alright, on Monday, we'll come in, we'll do a couple more example problems. If you have some questions relating to your lab, we'll do that. On Tuesday, we'll do some review activity. We'll be back then after Thanksgiving. Okay?
What do you do about our lab?
As promised, let me finish up here this example problem. Coming from page 210, this is question number 9, and I wanted to do this problem because it is similar to another one of the calculations that you have to do in order to complete the conservation of momentum lab. So it says, a 35-gram bullet strikes a 5-kilogram stationary wood block and embeds itself in the block. The block and the bullet fly off together at 8.6 meters per second. What was the original speed of the bullet? So, we're looking for the initial speed of the bullet. Things that we know. We know the mass of the bullet. It's given to us in grams, but we don't want masses in grams, we want them in kilograms. So we divide that number by 1,000, and we get 0.035. It gives us the mass of the wood block as 5.0 kilograms. It tells us that the wood block is stationary when the bullet runs into it. That means that the initial velocity of the wood block has to be equal to 0 because it's stationary. But it says because it embeds itself in the block and the block and the bullet fly off together, that means that we know the final velocity of the bullet, but we also know the final velocity of the wood block. They're exactly the same because they're stuck together. So, 8.6 meters per second, 8.6 meters per second. As far as the picture goes, here's the ground, wood block. We'll color that blue to be consistent with our writing. Okay? And then, I'm going to use this triangle as my bullet, obviously not to scale. Color that in red to be consistent with our coloring. So, here's the initial situation, right? Bullet traveling very quickly, block not moving at all. After the interaction, right? Afterwards, here's the block again. And the bullet, again, but now the bullet is embedded into the block. So they have become one object. They are moving, but much more slowly than the bullet was to begin with, or at least you would assume so. We're going to find that out when we figure out what the initial velocity of the bullet was. The interaction between the two objects results in an equal force, Newton's third law. So that means equal force, equal time momentum of the wood block. Together, those values have to equal the sum of the final momentum of the bullet plus the final momentum of the wood block. Again, to find the initial momentum of the bullet, you need to know the mass of the bullet plus the bullet's initial velocity. You add that together to the mass of the wood block times the initial velocity of the wood block. Those two values added together will give you the same number as the mass of the bullet times the final velocity of the bullet plus mass of the wood block times the final velocity of the wood block. So, going back to our list of things that we know and don't know, mass of the bullet we know. We don't know the initial velocity of the bullet. That's our unknown. But because we know the mass of the bullet there, we know the mass of the bullet there. We know the mass of the wood block. We also know the initial velocity of the wood block. It's 0. So this whole term will become 0 here. We know the mass of the wood block over here, and we establish, because they become embedded in one another, we know the final velocity of both of them. It just happens to be the same. So now we have an equation that we know all of the things except for the one thing that we're looking for. So you go ahead and you plug in your values that you know, and you'll be able to get the initial velocity of the wood block. Go ahead and do that. I will do that calculation as well. That's what I get when calculator there. Going back to our original numbers in the problem, looks like 2 sig digs there, 2 sig digs there. So we round our answer to 1,200 meters per second. This problem, when the two separate objects become one object, that's going to be similar to trials number 5 and 6 on your lab when you use the Velcro patches to stick the cars together, where they had initial momentum separate from one another, but their final momentum or the final condition has them being stuck together, so their final velocity should be the same. The previous problem that we did, with the two objects starting separate and ending separate, that's going to be similar to trials number 3 and 4 from your lab, where you use the magnets to send the cards towards each other and then watch them bounce off of one another. So those are the two example problems that are similar to what you're going to do in your lab. Now that you have your lab data collected, you can start working on those calculations. Okay? Also,